Awesome. Okay, so just a little recap. We were discussing linear transformations. The idea in the previous video was as follows. We had a vector space V and we had a vector space W, and we said that a mapping of vectors from this space to vectors in this space is called a linear transformation LT if it satisfies these two conditions. If it satisfies, first, L of alpha V is alpha L of V, where of course V is a vector that belongs in vector space V, and L of V is the image of this vector V in the vector space W, right? So this was the first condition, that a scalar multiplication should be mapped onto a scalar multiplication. And secondly, L V1 plus V2 should be L of V1 plus L of V2. That a vector addition should be mapped onto a vector addition in the other space, right? And so if we write these two together, they're basically saying that a linear combination in the first space should map onto a similar linear combination in the second space. That's something that we discussed in the last video. And something that I left hanging, I introduced in the last lecture, but I left hanging was we can represent, there's a relationship between linear transformations and matrix vector multiplications. So linear transformations Lx are closely related with the matrix vector product A times x, or you can even remove the parentheses, it's just Ax, where A is a matrix and x is another matrix, right? And so this is the relationship that we're going to explore in today's video or lecture or whatever you want to call it. Perfect. Awesome. Hello Farooq, hello Soha, hello Altamash. Welcome. Okay, so the idea for today is what's this relationship between linear transformations Lx and these matrix multiplications. So firstly, the simple thing to first notice is if you consider just matrix vector product, so every m by n matrix A when multiplied with a vector x of size n gives a linear transformation. And that's very easy to check. So what it's saying is that if you take any vector Ax, if you take a matrix of size m by n and you multiply it with a vector of size n, so this is m by n and this is n. So this entire result is going to be of size m. So every m by n matrix A when multiplied with a vector x of size n gives a linear transformation. And what linear transformation does it give? It gives a linear transformation from the space of Rn to Rm, because it's very easy to see that you're multiplying it with a vector in size in Rn. This vector was of size n, and you're multiplying it and you're getting the result which is of size m. So the linear transformation is from the space Rn, the n-dimensional real space, to the m-dimensional real space. And to establish this is very easy. The way you establish this is, of course, how do we check whether a transformation is linear or not? So if I say the transformation Lx is simply a times x, then it's easy to check that it's linear by the following method. You can just check whether a times alpha x1 plus beta x2 gives you alpha a times x1 plus beta a times x2. And this, of course, is very easy to see because it's just matrix multiplication, and matrix multiplication follows these rules. It's very easy to see. You can break this down by writing. So I can, perhaps I don't even need to show this, but let's do it for the sake of completion. So if you consider Lx as a of a times x, then the linear combination alpha x1 plus beta x2 will be mapped onto a times alpha x1 plus beta x2. And of course, this is just matrix vector multiplication. I can distribute this a times alpha x1. Remember that x1 and x2s are vectors. A times beta x2. Alpha, you can switch, take the scalar multiple outside and bring in the matrix vector product, beta a x2. And you can, of course, replace this by L times the linear transformation of x1 plus beta times the linear transformation of x2. So it's as simple as that, showing that every matrix vector product will give you a linear transformation. I'm going to pause for a couple of seconds, so let me know if all of this is clear. Also, if you've just joined and if you've missed some of the parts of what I was saying, you can, of course, this video will be posted on the channel, so you can review it afterwards. So whatever you've missed, you can cover again from the channel. Okay, so I'm assuming this is clear to everyone, and I'll move ahead. So we've just, for now, we've established that every AX is a linear transformation. But the more important thing is the relationship that goes the other ways, which is, can every linear transformation be expressed as a matrix vector product? And that's the important question, that, well, we know that every matrix vector product is a linear transformation, but the reverse question is more important, which is that can we express every linear transformation as a matrix vector product? So for whatever linear transformations that we saw in the previous lecture, can we express them simply by a matrix vector product? So the question is, can we find A for every linear transformation such that L of x can simply be expressed as A times x? Okay, and so the quick, short, simple answer is yes, you can find such an A. And let's do that first for a very specific case. First, let's consider linear transformations from the space Rn to Rm. And we have a simple theorem that says every linear transformation from Rn to Rm can be expressed as Lx equals to A of x, sorry, A times x. It's the same thing, but just more notationally correct, where A is an n is an m by n matrix. Right? So how do we find it? A is given as, if I write A as columns, so let's suppose A1 is the first column, A2 as the first column, and so on. A will have n columns here. So I'm basically writing A as column vectors A1, A2 up until An. If you express it like this, then each column is nothing but the effect of this linear transformation on Ej, where j of course goes from 1 to n, because the original space is n dimensional, and so I will have n standard basis vectors, where Ej, j 1 to n, are the standard basis vectors of Rn. Okay. So I've just claimed that if you take a linear transformation, this theorem is telling you that if you have any linear transformation from an n-dimensional real space to an m-dimensional real space, all you need to do to find this matrix A is just find out what does this linear transformation does to the standard basis vectors, and start from 1 to n, find out the effect, what it does to, so A1 will simply be L of E1. So the first column, just find out what's happening to the first standard basis vector, transform it, and so this will give you the first column. Then A2 equals to LE2 will give you the second column, and then you can construct, this is the construction, this is telling you how to find A. And we'll do an example of where I show you how to construct this A. But first let's prove this theorem so that we can use it. So let's prove this theorem. So we have a proof. We have a linear transformation going from Rn to Rm. Let's suppose x belongs to Rn. Then of course L of x is the linear transformation. Since x is a vector in Rn, then you can of course express x as x1 e1 plus x2 e2 plus up until xn en, which is nothing but your simple statement from the definition of basis vectors, that if you have a set of basis vectors, you can express any vector in that space as a linear combination of your basis vectors. And so I will replace x by x1 e1 plus x2 e2 plus up until xn en. And now all I need to do is use the property, because I know since L is a linear transformation, I know this for a fact because we started off with a linear transformation, then I can use the properties of linear transformation. That is, addition in this space, in the original space, will turn into addition in the output space. So Lx E1 E1, I can separate the additions Lx2 E2 up until Lxn En, and again we apply the definition of a linear transformation, that a scalar multiplication in the input will become a scalar multiplication in the output. So x2, remember that these are vectors, e's are vectors and xi's are scalars. So Le2 plus up until Len, right? Xn Len. And now at this point I will define some vectors. I will define vectors Aj, these are the column vectors that I needed, and I will define them as Lej. So what I'm saying that this is A of 1, this is A2, dot dot dot, this is An. And if I do that, I have x1 A1 plus x2 A2 plus up until xn An. And if you recall that in the first few classes we did, that we showed that a linear combination of vectors is just, can be expressed as, this is nothing but, this is a column vector. A2 is a column vector. Xn, this is a column vector. This can simply be written as A1, A2 column vectors, An times this vector x1, x2, xn. So this is nothing but Ax, where A is given by the columns of A are given by this definition. And that ends the proof. What have I used here? I have just used the fact that summation xi ai I goes to 1 to n is nothing but the matrix vector product. This is something that we already know from previous classes. Let me know if this proof is clear. I will wait for a few seconds so that you can answer, I can answer any questions that you have, and then I'll move ahead with a few examples. So let's say example 1. Let's consider a linear transformation from R3 to R2. And the linear transformation is given as Lx equals, the first coordinate is given by x1 plus x2, and the second coordinate is given by x2 plus x3. So this is the result of this linear transformation. So for example, what this transformation is saying is that if you have a vector x1, x2, x3 in this space, it will become the vector x1 plus x2 and x2 plus x3. So this 3 vector will become a 2 vector. Okay. Thank you, Abdul Qureshi, for replying. Thank you, Ramasa, for replying. Okay, so this 3 vector becomes a 2 vector. And the question is, again, find A such that Lx can just be written as A of x. So I want to convert this linear transformation into a matrix vector product. And to do that, we have the previous theorem. The previous theorem told us simply, hold on. So the previous theorem told us that to find this matrix A, all you need to do is to find, first let's figure out the size of this matrix. So if this is Rn to m, then this matrix will be 2 by 3. So A will be a 2 by 3 matrix, because it should be able to be multiplied with a 3 vector and the result should be a 2 vector. Right. Okay. So we can construct A by finding the columns A1, A2, so it has 3 columns, A3, we need to find 3 column vectors. And the way we find that is we have Aj equals ej. So we just need to figure out what happens to the standard basis vectors. So my space is R3. My space linear transformation is from R3 to R2. And so the three basis vectors that I have are E1 as 1, 0, 0, E2 as 0, 1, 0, and E3 as 0, 0, 1. So we just need to figure out what's happening to the standard basis vectors. Okay, so A1 is given by L E1, A2 is given by L E2, and A3 is given by L E3. Okay, so what I need to do is figure out what happens to this vector. Let's write down the transformation again. The transformation was that x1, x2, x3 is mapped onto x1 plus x2 and x2 plus x3. So when I apply this on 1, 0, 0, the result is x1 plus x2, so 1 plus 0 is 1, and 0 plus 0 is 0. So this is A1. Similarly, if you apply this to 0, 1, 0, then this is 1 plus 0 is 1, and 1 plus 0 is also 1. This is A2, and L of 0, 0, 1 is simply 0 plus 0 is 0, 0 plus 1 is 1, and this is A3. So these are the three columns of my matrix, and I can check. I can make the matrix A as the first column is 1, 0, the second column is 1, 1, the third column is 0, 1. And this should give me a matrix vector multiplication. So I can express Lx as equals to A times x. Let's not be too confident, and let's just verify that this is true. So if I multiply A with x, where x is simply x1, x2, and x3, if I multiply 1, 0, 1, 1, 0, 1 to x1, x2, x3, what do we get? The first column will be this row multiplied by this column. So 1 into x1, so x1 plus x2 plus 0 times x3, which I don't need to write, but we can still write this. And the second row will be 0 times x1, which is 0, plus 1 times x2, x2 plus x3. And you see that the result is exactly the same as the transformation that we were trying to express. So you don't need to express L as, x1 plus x2. You don't need to write it as this. You can simply write it as this matrix times any vector from the original space. There is another example that I want to show from the book. Which is as follows. Okay, let L be the linear transformation operator R2 that rotates each vector by an angle theta in the counterclockwise direction. So what we have is essentially we have a linear transformation. So the linear transformation is given as, what it does is simply a counterclockwise rotation. So if you have a vector x in R2, let's suppose this was the vector, the transformation that we have, L, will map this vector onto this vector. It will rotate it by theta degrees. So angle of rotation is theta. This is the angle of rotation. And this new vector is L of x. And the question again is, how do we express this matrix, this linear transformation as A times X? What's A here? And of course, you can use the theorem, and if you use the theorem, you know that A is nothing but what happens to the standard basis vector. So A is simply L of E1 and L of E2. These are the two columns that you need to find. Why are these two columns? Notice that A takes a vector from R2 to R2. So L takes a vector from R2 to R2. So A will be a 2 by 2 matrix. It's a 2 vector that's mapped onto another 2 vector. It's actually a linear operator. And so the way you do that is to simply see what's happening to the standard basis vectors. So notice this, these are the two figures that will help us see. So first notice that if you take this 0, 1 vector and if you rotate it theta degrees counterclockwise, then this vector is mapped onto this vector. And you can apply a bit of geometry and see that the length of this vector is minus sine theta and the height of this vector is cosine theta. And similarly, if you take the other standard basis vector, this was E1, this was E2. E1 will be mapped onto cosine theta, sine theta. You can check that the height of this, I won't do this for you, you can apply a bit of trigonometry and check that this is indeed correct, that the height will be sine theta and the length will be cosine theta. And for this one, the length will be minus sine theta because it's in the negative x-axis, and the height will be cosine theta because this is the angle. And so if you check, so what's happening is essentially for E1 the result is cosine theta sine theta, and for E2 the result of the transformation is minus sine theta cos theta, and this is your matrix A. So this is the matrix of rotation by theta I was going to say something that I forgot, in the anti-clockwise direction. So now if you have any vector in R2, let's suppose 3, 4, and if you want to rotate it theta degrees in the counterclockwise direction, all you need to do is multiply cos theta minus sine theta, cosine theta by this, and the result that you will get will be the result of rotating 3, 4 vector theta degrees in the anti-clockwise direction. And of course, this can be theta radian if you want to do it in radian, if it can be degrees if you want to do it in degrees, because sine theta and cosine theta, as long as you're taking the correct trigonometric ratio for degrees and correct trigonometric ratio for radian. And so we've done an example in which we were doing a transformation from a n-dimensional real space to an m-dimensional real space. And that was in a specific example, but it gives us a hint in what to do when we have general vector spaces. So for example, V is any general vector space which is mapped onto W vector space. So let's draw a diagram. This is vector space V, this is vector space W, and L is mapping vectors from this space into vectors of this space. And the assumption is that L is a linear transformation. For example, a general vector space could be as follows. Let's suppose V is C AB, that is continuous functions defined on the interval AB. And let's suppose L is the transformation Lx, or rather Lf of x, simply is the definite integral AB of f of x dx. So essentially L is a linear transformation from the space of continuous functions defined on the interval AB, and it's mapping them onto some real number. So the result of a definite integration is just a real number. So this is my space V and this is my space W. And now these are no longer vectors in Rn or vectors. Well, this space is still some vector in Rm, but what about this space? It's not a vector in Rm. And so we need some other way of expressing this linear transformation. And the question is, can we find some matrix A, and can we express this as Lx equals Ax, which should be a little confusing if you're following the logic of the previous theorem, because now V is not Rm, so how would we even describe this? But let's suppose we're describing some general space. Let's suppose we have the following condition. Suppose you have V and W are vector spaces, and E equals V1 to Vn is a basis for V, which basically means V is n-dimensional. So V is an n-dimensional space. And let's suppose we have another basis F, W1 to Wm is a basis for the vector space W. So W is m-dimensional. So what you have, first let's discuss something interesting, which is if yes, Saad, I will share the pictures of these notes and I'll upload the notes in the Drive, Google Drive folder. Okay. And so first let's understand this. If let's suppose V is a vector in this space, in vector space V, then V can be written as x1 V1 plus x2 V2 plus so on xn Vn. And if W is a vector in the vector space W, then it can also be expressed as a linear combination of the basis vectors plus y2 w2 plus up until we will need m vectors now, m wm, right? So notice that even though v1 v2 up until vn and w1 w2 up until wm, these are not vectors in Rn or in Rm. So V1 is not a member of Rn, and similarly, Vi's are not members of Rn, and similarly Wi's are not members of Rm. These are not real dimensional vectors. They can be functions, they can be matrices, they can be polynomials, they can be anything, right? And so, but these x1, I can make a vector x, which is x1 to xn, and I've made this vector in previous classes as well, and I've called it the coordinate vector of V with respect to the basis E. So essentially what we've said is that x is actually the representation of V in terms of the basis vectors E. So if you have these scalars, you know what vector V is, because V is simply the first scalar times V1, the second scalar times V2 up until xn and Vn. And this vector that we've just made is a member of Rn. And the vector y, which is an expression of W in the basis F, is also a vector in Rm. So even though we were talking about general vector spaces V and W, these scalars that are given by their representation in some basis are indeed vectors in Rn and vectors in Rm. So this gives us an idea that maybe we can find some matrix A that goes from Rn to Rm, and here's the theorem that I will state before I prove, which is that if you have, let's bring this up, and the theorem is, yes, here it is. The theorem says that Ax equals y if and only if LV is this. What is it saying? That if I can express, I can say x is equals to Ax equals y, I can find this matrix A if and only if L of V is y1 w1 plus y2 w2 plus ym wm. To repeat this idea, the idea is saying that if you had a vector v that was being mapped onto vector LV, then v is a vector in this space, and you can write v as x1 v1 plus x2 v2 up until xn vn. So x is a coordinate vector for this vector v, and LV, let's call this vector w. This vector is in vector space W, which means it can be written as a linear combination of the basis vectors of W. So LV can be written as y1 w1 plus y2 w2 up until ym wm. And so if you can do this, then there is a matrix A that if you multiply it with the coordinate vectors of V, you will get the coordinate vectors of W. You will get the coordinate. So there exists A, which is an m by n matrix such that Ax equals y gives the coordinate vector of L of V with respect to the basis F. This will be more clear when we go through the proof, but for now this is the statement that you can take a general vector space, a linear transformation from general vector spaces, and you can express it as a matrix vector product of not these vectors but of their coordinate vectors. That's the important thing to remember, that this x and this y are not in V and W. X is not in V, x is an n vector, y is an m vector. X was given the coordinates of this vector in terms of basis E. Y was giving the coordinates of this vector in terms of basis F. And this is the relationship between the two coordinate vectors. And we can always find such in A. And so the question remains is, what is A? How do we find it? And the hint of that comes from the previous example. The previous theorem that we did gave us what's going to happen. So let's write this down a bit more. Let's state what we're talking about very clearly. We have vector V, vector space V, which has a basis E V1 to Vn. We have a vector space W with bases F W1 to Wm. We have a vector V in vector space capital V, and if we have this vector, we can express V as x1 v1 plus xn vn, such that we can say x is equals to the expression, the representation of vector V in basis E. Okay. So let's start this. Let's start to construct matrix A. And the hint is, all we need to do is check what happens to the basis vectors. So what's happening to these Vj's under this transformation? So, okay, let's find out what's happening to L of Vj, where Vj is a basis vector from this collection. So I'm taking j can be between 1 to n. Well, I know that this vector has to belong, this vector that I've just written, if I transform this, L takes my, L is a linear transformation from V to W. That means L of Vj is going to be a vector in W, which means I can express this vector as A1 j W1 plus A2 j W2 plus up until AM j Wm. I've noted this j because we are talking about the coordinate vector Vj. So L of V1 will actually be A11 W1 plus A21 W2 plus so on, AM1 Wm, right? Similarly, L of V5 could be A15 W1 plus A25 W2 plus up until AM5 Wm. So this j keeps track of which basis vector we are talking about from space V, and this is the representation of that vector in the space W. Okay, so I can shorten this expression and I can write LVJ is simply summation of Aij Wi. Notice that this is I, j is fixed, and the summation is going from I 1 to m. Okay, so I've just shortened this down. So this is what's happening to the basis vector, the standard basis vectors. This is what's happening to them. Okay, now let's consider this matrix. Let's make a matrix. Construct matrix A, which is made up of Aij, such that every column is A1, A2 up until An, where I'm defining these A1s, A2, An as columns. Is that clear? So in column form, I have written these down, so I can expand this actually and write this matrix as follows. The first one is A11, A12 up until A1m. So this was the LV1. So notice that this is just L, the scalars from LV1. Similarly, you have LA21, A22 up until A2M, and similarly this goes on. Okay. All right. Actually, I should have written this as A1, 1, 2, 1, and M1, because J is fixed and I is changing, so this is 1, 2, 2, 2, M2. Similarly, A1, 3, and I goes 1, 4, sorry, 2, 2, 3, A2, 3 up until AM3 and so on. So these are the columns. So A1 was given by this, A1, 1, 2, 1, blah, 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 and so on. Okay. This is the matrix that we've constructed. And so let's check this out. Now, we're not interested in the coordinate basis vectors. We're interested in what happens to some general vector v in the vector space capital V. So if I want to find L of this vector, this is simply L of, since this vector is in coordinate space V and I have a representation of this vector in terms of vj's, then I can simply write this down as summation xj vj. J goes from 1 to n. All right. So this is the linear transformation. These are vectors, these are scalars, and this is just a sum. So this is nothing but a linear combination, this linear combination that I've just written as summation xj vj, j goes from 1 to n. Okay. And so this is a linear transformation, which means I can take the linear transformation inside the scalars. A linear combination in input will give me a linear combination of the output. So I can simply express this as summation j equals 1 to n xj L of vj. So the question is, what is happening to the standard basis vectors? And that's something that we've already established. We know what's happening to them, and we've written it down in terms of these coefficients. So I can take this LVJ and I can write this as summation on j xj and another summation in I, which goes from 1 to m of a ij wi. So this is scalars, these are scalars, these are vectors. And so since we have scalars, we can rewrite the summation as summation j summation I as xj aij wi, right? And now notice something important. We can switch this j and I, which means it can be written as summation I and then summation j xj aij wj, sorry, w of I. So this summation that's happening on j is only on this x and on this aij. So we can sum over j before we can sum over I, and you can write wi outside. This is wi. Wi can be written outside the summation because it doesn't contain the j index. And so what we have essentially is the following. What we have is that we have represented L of v as summation I summation j xj aij wi. Now notice that taken together, this is just a constant. For every I, this is just a constant. So if you fix I, you first sum over j and then you take. So these can be expressed as yi's. These are scalars. So for example, y1 is simply summation x j, a1j, j goes from 1 to, sorry, I goes from, sorry, j goes from 1 to n. Similarly, y2 is nothing but summation j xj a2j, and so on and so forth. So what we're getting is these constants y1 to y2, and how many constants there are? Since I goes from 1 to m, there are m scalars y1, y2, ym. And notice that if I write this in this form, summation yi wi, then our job is done, because what we've done is we've represented LV as y1 w1 plus y2 w2 plus up until yn wm, which was the statement of the theorem, which is something that we started off with. So that was the statement of the theorem, and we found that LV is actually equals to this, these coordinates, where these coordinates y1, y2 up until ym are actually given by this thing, which is summation xj a1j, and you can actually express this y vector simply as y equals to a summation of the following form. You can write this as summation j goes from, if I can express these as column vectors, then this is just summation j goes from 1 to n of the vector x times a j. So aj is essentially the column vector that we found initially, and x is nothing but x1, x2 up until xn, and this was nothing but y1 to ym. And so after all of that work, we've just noticed that this is nothing. Y has been expressed as x1 a1 plus x2 a2 plus up until xn an. So it has been expressed as a matrix vector product, where we've again used the fact that if you write this down as a linear combination of the columns, then a linear combination of the columns is nothing but the matrix vector product, where the matrix is given by these columns a1, a2, an. Okay. This is called the matrix representation theorem. So let me restate the theorem. What's the theorem? Or rather, we can just look it up in the book. So the theorem is as follows. The theorem states that if E is the basis for V, capital V, and F is the basis for capital W, and you have a linear transformation going from V to W, then there exists a matrix M by N matrix A, which if you multiply this matrix by the coordinates, so what's essentially they're saying that if you can write, if X is the coordinates of V in the basis E and Y are the coordinates of L of V in F, then simply Y is equals to A times X, which is that the coordinates of LV in F basis are given by multiplying A to the coordinates of this vector V in E basis. So that's the relationship that we're given. And furthermore, if we look at this, then what they're saying that A is the matrix representing L relative to the ordered bases E and F. And in fact, you can just simply find the columns AJ by finding out what's happening to the basis vectors. So if you just find out what's happening to the basis vectors under L, then that will give you the columns for matrix A. Okay. Okay. So since there's no questions, let's move on. Okay. So here is the next example. Let's say, and this is just an example that we're going to do from the book, which was L is a linear transformation from R3 to R2 under where Lx is given as x1 b1 plus x2 plus x3 b2, where b1 is actually 1 1 and b2 is actually minus 1 1, and basically b1 b2 is also a basis for R2. Okay. So what's happening here? We have the space V is R3. The basis that we have for the original space is simply the standard basis vectors E1, E2, and E3. And W is actually R2, and the basis that we have for R2 is B1 and B2, not the standard basis vectors of R2, but these vectors that we're dealing with. And the question is, what's A? Can we find A such that Lx is Ax? And of course, A is simple to make. A has one column and another column. So if this was going from a 3 space to a 2 space, so actually there should be 3 columns, A3, and the size is going to be 2 by 3. So it should be able to be multiplied with a 3 vector and get a result of A2 vector. And so A times X, and so the way we will find this is A1 is actually the result on the first standard basis vector, A2 is the result on the second standard basis vector, and A3 is the result of L on the third basis vector. So we just find A1, A2, and A3. And that's simple to do. E1 is simply 1, 0, 0, transform. And so if I find LE1, that's simply x1 b1, which is simply 1 b1, plus x2 plus x3, which is 0 b2. So the coordinates that I have of LE1 under b1 and b2 are 1 and 0. So y1, so the first coordinates that I'm getting, a1, is actually, so a1 is simply 1 0 transpose. Similarly for E2, it's simply 0 1 0 transpose. If we find the effect of the linear transformation, we have, so what was the transformation? It was x1 b1 and x2 plus x3. So x1 is simply 0 b1 plus 1 plus 0, which is just 1 times b2. So a2 is nothing but 0 comma 1, and finally E3 is 0 0 1 transpose. LE3 is simply 0 b1 plus 1 b2, and so A3 is simply 0 1 transpose. So the matrix for this transformation, if I can write it column wise, what was it? It was 1 0 0 1 and 0 1. So matrix A for this transformation is actually A1, A2, and A3, which is equals to simply 1 0 0 1 0, 1. Yes, Harun, don't worry. I will be posting these notes on the Google Drive, as well as this entire live stream will be posted on YouTube immediately after the lecture. So don't worry about getting this notes and getting the lecture. Okay. So that's how we find the transformation for this. This is the matrix A. So Lx is simply A times x. That's the linear transformation. Okay, so couple more theorems, which I will just state without proof. And so the first theorem is, let's just go to the book and understand it from there. So the next theorem that we're interested in is, you can do these examples on your own. I'm leaving this for you. Okay, here's another theorem. This tells us that if you have a basis for the first vector space Rn and another basis for Rm, so u1 to un is the basis for this, and b1 to bm is the basis for Rm. And if you have a transformation that takes an n vector to an Rm vector, so we're no longer talking about general vector spaces, we're talking about a specific n-dimensional vector space, the real n real dimensional space, and a transformation that takes it to an m-dimensional real space. So if this is a linear transformation, you can again construct A, and this time the construction of A will be done by, so these are no longer standard bases, these are bases E and F, and this transformation is given by a vector whose columns are given by this. So it's just very similar to the previous example, except not only are the columns equals to L of uj, but you also have to multiply it with B inverse, where B inverse is the inverse of this matrix. So what do? You first make a matrix B whose columns are B1 to Bm. And then you find the inverse of that matrix and you multiply it with L times uj, where this is the effect of what happens to this basis vector Luj is basically the result of the linear transformation on each of the basis vectors, right? And so I'll leave the proof to you. You can do this on your own. But instead of doing this, finding the inverse, there's an easier way to find this matrix. And the easy way to find this matrix is follows, which is given by this corollary. If A is the matrix representing the linear transformation with respect to these two bases, the one that we did in the previous theorem, then the reduced row echelon form of B1 to Bm augmented with Lu1 to Lun is Ia. So let's just write this down and see what it says. It says that if you make a matrix B1 to Bm and augmented, so these are columns, B1, Bm, these are just columns, these are just the basis vectors of where B1 to Bm are the bases of Rm, and Lu1, Lu2, Lun, these vectors, so u1 up until un was a basis for Rn, and these things, these vectors are actually Lu1 is the transformation, or rather Lui is the transformation of ui with respect to L. So to find A, all you need to do is make a matrix whose first m columns are these basis vectors, whose next n columns are the transformation of the base of these basis vectors. And then the next step is just to find the reduced row echelon form, which you should all know. Then this gets transformed into I augmented with A. So the first m columns will give you the identity column, the identity matrix, and the next n columns will just give you the matrix A, where L is a transformation from Rn to Rm, and therefore A is an m by n matrix, which is easy to see because you have n columns, because you have LU1 up until LUn, and each of these transformations will lie in Rm, so they will have m rows. Okay, so these are the two important theorems that you need to know. I'm leaving the proof for you to explore. If you have any confusions, let me know. But that's all of the theory that we'll discuss. There is a couple more examples that I want to go through. So you can do this example on your own. Here is something about computer graphics. So let's suppose if you want to stretch something, if you have a transformation Cx, and if you want to find the matrix of this stretching, just find out what happens to the standard basis vectors E1 and E2. Similarly, if you want to reflect about an axis, then again just figure out what happens to E1 and figure out what happens to E2 and write that as columns. If you want to do a rotation like we did before, you can just find out what's happening to E1, what's happening to E2. If you want to translate something, then again figure out what happens to E1, what happens to E2, and write that down. Another example is this example where you have this stick figure representation, and you can represent this, think of this as a picture. This is a picture, right? And you can represent this as a 3 by 81 matrix. Let's suppose there are n rows, n pixels here and n pixels here. Let me actually do this for you. So let's suppose you have an image such that you have 9 pixels in this direction and 9 pixels in this direction. And if you have some image, let's suppose this is your image, then you can actually represent this by a 3 by 81, 3 rows and 81 columns, where the first 2 rows, this will give me the x1 and y1. So the first coordinate, this is the coordinate of the pixel, and the last row tells me whether this is black or white. So if it's black, maybe there is stored 1, if it's white, if it's 0. So the way this image will be stored in your computer is using this matrix. So if I can, let's suppose I have this matrix, let's just make a matrix 1, 1, next will be 1, 2, 1, 3, let's suppose these are the coordinates. And if let's suppose this was 0, this was 0, this was 1, this was 0, this was 1. So if this is the matrix, I can make an image out of this matrix as follows. Let's suppose this is my canvas. I know that there are 81 columns, so this is 9 rows and 9. And so the coordinate 1, 1, I will check whether to shade this or not. This number is 0, so I won't shade it. This number is 0, I won't shade it. The next one is 1. So on the third coordinate, I will shade it. And then in the next coordinate, I will leave it blank. The next coordinate, I will shade it. So similarly, just as these two are black, I can make this smiley face image as well, where only these coordinates, these points, the coordinates of these points will have ones, and all the white space that you see, the one that is not shaded except this smiley face, everything inside the smiley face and outside except for this two, these will be zeros, expressed as zeros in the third row, and this boundary and these points will be expressed as 1 in this matrix. So this is how you can represent a two-dimensional image using a matrix of size n by whatever, 3 by whatever size of canvas you have. So this stick figure image can be represented as a 3 by 81 image. So these coordinates 0, 0 will be 1, and then the next one you can figure out which coordinates are 1 and which coordinates are 0 based on this image, right? And so if you want to translate it, then this example tells you how to translate it. If you want to take this image, if you want to take this stick figure over here, you need to figure out how to do a translation, which is given in this example. And I want you to go through this on your own. There's another example where you think about the rotation of this aeroplane. If it's moving in this left, right, if it's tilting in this direction, or if it's tilting in this direction, or if it's tilting in this direction, that can all be expressed by a linear transformation. Yeah. So that's it. And you can go through these examples on your own. That's it for the class. Let me know if you have any questions. I'm going to wait for a few minutes, and if you have any questions. Grading plan. Okay, before I get to the grading plan, I wanted to tell you that the assignment 3, I have it. I will edit it a bit before I post it on the Piazza folder today. Grading plan, I am not sure. I'm going to replace your midterm by probably some project. So the only thing that I think is feasible as a midterm now is I will give you individual projects and you can choose the topic on your own, or I can assign topics to you. But the idea is I want an individual project from each one of you as a replacement for your midterm. So if I recall correctly, your midterm was 20%. So this project will be 20%. I might change the weightage a bit depending on how well you do these projects. And the final, so IBA is a bit optimistic in that we can have exams in June. So if that's the plan right now, if we can have physically available exams in the classroom, in the examination room, we'll have those exams. But if we don't, then again, maybe I'll have another project for you in the final as well. Something that I think Dr. Said Ghani wanted me to tell you was that let me look at the email. They're going to have an academic meeting tomorrow of the academic committee where they will decide if, let me see what they will decide tomorrow. Here is the email, blah, blah, blah. Okay, you may be, blah, blah, blah. Okay, so tomorrow they will discuss whether we'll have the option of pass-fail or not. So if we have options of pass-fail, then we'll implement that. But tomorrow they'll be discussing some grading options. So you will know more about that. Murtaza, I am very well. Thank you for asking. Any other questions? Let me also know if the current setup for these lectures is fine, if you can hear me and view the thing properly. I personally think this is the best option for us. I have tried this in my discrete math course as well, and they seem to be quite happy with the current setup. But if you think it can be improved in some way, let me know and I'll try to fix some issues. Okay, Dania, you're not enrolled in the class, so unfortunately your opinion does not matter here, but thank you for saying that. Anyone else who's enrolled in this class and has any opinion about whether this setup works or not? Sure, I will. That's something that I will consider. If you do good projects, then I will be very willing to increase the weightage of the midterm project and reduce the weightage of the finals. Yes, Murtaza, we can run as many experiments as you want after this class. Can I? Yeah, thank you. Anyone else? No. Should we fade to black then? Nope. Okay. Thank you, everyone. Have a good day. And see you on Wednesday. By the way, we'll be following the regular schedule now. Wednesdays, 4 p.m. will be our classes, just like your schedule at IBA. Nope. No feedback, no questions, no nothing. Okay, cool. Bye-bye.